Hello, good day, good afternoon, Chem Kids. We are talking about acids and bases. Last week we talked about molarity. Today we're going to talk about acids and bases, and next week we'll kind of revisit that molarity when we do pHs. But for right now we're talking about acids and bases, so let's start by defining our acids and bases. Our very first definition of an acid and base came from Arrhenius. Arrhenius did a lot of work with solutions, and he defined an acid as a substance that creates an H plus in solution. All right, so an acid is one that creates an H plus. So then a base at that point is a substance that creates an OH minus. And this worked for a few years, but then we had to kind of figure out, other scientists came along and they had to expand the definition because this was very limited. The Arrhenius acid and base definition was pretty limited to only substances that contain H's and OH's. So what they had to do was kind of revamp it, and that's where Bronsted-Lowry came in. Bronsted-Lowry is the one that we're going to use most often. There is actually another theory on acids and bases definitions, but we're not going to use that in this class. So our definition that we're going to use most often is a Bronsted-Lowry acid is one that donates an H plus. And we can also call that a proton, because if we're talking about an H plus, that's a hydrogen that has lost an electron, so it's only a proton. So you might hear it both ways. You might hear an H plus, or you might hear proton. Then a Bronsted-Lowry base is one that accepts the H plus or a proton. So in this case, we're talking about acceptor and donator, and this broadened our definitions of acids and bases, and it became a little more easy to define acids and bases. A couple other words that we need to get in here before we go on and start assigning them is we have a conjugate acid. A conjugate acid is, I'm going to say, the former base. So it used to be the base on the reactant side. I'll put reactant there. All right. And this is one that has gained an H plus. All right. So on the product side, it is gained an H plus, and you'll see that in just a little bit. A conjugate base then is the former acid. And again, this is on the reactant side. So it used to be an acid, and it's not anymore because it's the one that donated the H. All right. A conjugate acid base pair is one that only differs by H pluses. All right, they're only different by an H plus, and we'll see that in just a little bit as well. And then we have our word amphoteric here. Amphoteric, our prefix ampha means either or. All right, so amphoteric means it can act as an acid or a base. So it can act as an acid or a base. Okay, now let's see if we can't kind of do some problems here that'll look very similar to what our homework is. So if we look, it says, what are the conjugate acids? Up here, our definition of an acid is the former base, and it's gained an H plus. So we're going to add an H plus to each one of these. So if I have OH minus and I add an H to it, I'm probably going to get H2O, right? Now with the charge thing, we have -1 and we're adding a positive, so a negative plus a positive, no charge, so it's just H2O. All right, so let's look down to the next one. We have HCO3. Again, we're trying to add an H plus to it, so now we'll have two H's, H2CO3, and now checking our charge, we're going to take a negative and add a plus to it, which gives us no charge there. All right, hopefully that makes sense. Okay, now moving down to B here. This time we're finding our conjugate base, and remember our conjugate base is one that we've donated an H plus, so we're going to take an H plus away from each of these. So we have H3O plus. If we take an H away, just one H, we're going to have H2O, right? And if we take a positive away, remember, check our charge. If we take a positive away, it's just going to be no charge, right? We could put a 0 up there, but that would be kind of weird. We don't do that, so we just leave that off, but we know it has no charge. Okay? So now let's go to the next one. We have HCO3. Again, take an H away, leaving us with CO3. Now, if we took a positive away from a negative, so we already had -1, and we subtracted 1, that gave us -2. So our charge on this one is -2. All right? Awesome. Now, in this last example, we're going to put it all together. We're supposed to identify the acid. I'm going to change colors on this. The base, the conjugate acid. Let's go blue there. Our conjugate base, go green. And our conjugate acid base pairs, we'll do that in just a second. So remember, our acid is the one that donates the H. And it's also going to be on the reactant side. Okay, so remember, this side, draw an arrow here, this side is our reactant side. So which of these two, HF or H2O, over here, or on the product side, has lost an H? And if you look, HF became F minus, so it's the one that lost the H. So we're going to label HF as our acid because it lost the H. Okay? Now shifting gears, if we go to our base, remember our base is the one that gains the H plus. So if we look, water on this side has 2 H's. On the right side, it has 3 H's. So this is my base, H2O. And both of these are on my reactant side. Okay? Now if we go to our conjugate acid, this is always going to be on our product side, and it's the one that gained the H plus. So which one of these, H3O plus or F minus, gained the H plus? Yeah, that's right, H3O plus. So this is my conjugate acid, and I'm going to abbreviate CA, all right, conjugate acid. So my conjugate base is the former acid, or it's the product side of the acid, which now it became a base. So we're going to say this one is my conjugate base. Okay? And the last part there, the conjugate acid-base pairs, let's put that one in pink. All right? The acid goes with the conjugate base. All right? And the base goes with the conjugate acid. That's a conjugate acid-base pair. All right? I hope that makes sense. Thanks. See you next time.